You may or may not have heard of this word, paradox. It seems to be a concept in philosophy if you've heard of it, but what we're doing today is to explain its relationship with mathematics. So, the first question we have to ask ourselves is, what is a paradox? Let's look at the origin of this word. The English word paradox comes from the Greek word paradoxon, which is actually made up of two parts, para and doxa. Para means beyond, and doxa means belief. So, a paradox is beyond our belief. It's unbelievable. Okay, I guess that I didn't solve the problem. What exactly is a paradox? Let's read this definition. A paradox is a statement that, despite apparently faded reasoning from true premises, leads to an apparently self-contradictory or logically unacceptable conclusion. To make it simple, we can say it's basically an unsolvable mystery. Well, some are indeed unsolvable, but some are just seemingly unsolvable. Before looking into some examples, we'll see how they are classified. In 1962, philosopher and logician Willard Van Orman Quine distinguished between three types of paradoxes: veridical, falsidical, and antinomy. A veridical paradox is a statement that seems to be false but is proven to be true, while a falsidical paradox is a statement that appears false and is false but is once proven to be true due to a fallacy in demonstration. The most common and well-known type of paradox is called an antinomy, which is a statement that reaches a self-contradictory result, which means it can't be true and it can't be false. Let me give you an example of an antinomy, the liar's paradox. It consists of one simple sentence. This sentence is false. Seems easy, right? Let's look into these two cases. If the sentence is false, then the statement, this sentence is false, which means that this sentence is actually true. Wait, that doesn't make sense. What if the sentence itself is true? The statement, this sentence is false, would be true, which means that this sentence is indeed false. This makes no sense either. So as we can see, the statement, this sentence is false, can't be true and can't be false. This situation is what we call a self-contradictory conclusion. As there are so many paradoxes in the world, we cannot cover all of them in this program. Therefore, we'll focus on two of them which closely relate to mathematics. They include the Zeno's paradox, also known as the dichotomy paradox, which is about a tortoise and a Greek hero, Achilles. This paradox introduces the concept of infinity and infinitesimally small values. The other is called the Russell's paradox, which is a story of a barber. It introduces the concept of set theory. The show is about to begin. Are you ready?
Achilles, I dare you to a race. I've been thinking and I have come to a conclusion that I would win if you give me a small head start.
You are heavy and slow. You can never beat me. How big a head start do you need?
10 meters will do, thank you.
You will surely lose, my friend. But sure, why not? We'll have the race.
I will win. I will prove that my theory is right.
Okay, let's do it. But why do you think that you can beat me?
Very well, I shall tell you my theory. Suppose you give me a 10-meter head start. You say that you will cover that 10 meters between us very quickly.
Very quickly.
And in that time, how much should I have gone, do you think?
Perhaps a meter no more.
Very well. So now there is a meter between us. Would you catch that distance up very quickly?
Very quickly indeed.
And in that time, I should have gone a little way further. So now you must then catch the distance up. Yes?
Yes?
And while you are doing so, I shall have gone a little way further. So now you must then catch the new distance up. And so you see, in each moment, you must be catching up the distance between us. And yet, I, at the same time, will be adding a new distance, however small, for you to catch up again.
Indeed, it must be so.
And so you can never catch up.
You're right, as always. I shall never beat you. I give up.
Today I'm going to talk about the Russell's paradox. The Russell's paradox is also known as the barber's paradox. It starts off like this. There's a barber in town who said that he would only shave those and only those who do not shave themselves. The question is that does he shave himself? There are only two possible answers to this question, yes or no. We will look at these answers respectively. If the answer is yes, this means the barber should shave himself, since the claim indicates that the barber shaves those only who do not shave themselves. The barber should not shave himself. If the answer is no, that means the barber doesn't shave himself. Since the claim indicates that barber shaves those who do not shave themselves, the barber should shave himself. These two answers lead to contradictions. Before we solve this paradox, we should take a look at the set theory. The set theory begins with a fundamental binary relation between an object A and a set B. If A is a member or element of B, this notation is used. Since sets are objects, the membership relation can relate sets as well. The binary relation between two sets is the subset relation, also called set inclusion. If all the members of set A are also the members of set B, then A is a subset of B. For example, we have set 1, 2, 3. Possible subsets are nothing, 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, and 1 and 2 and 3. Union of the sets A and B is the set of all objects that are member of A or B or both. For example, set A and set B. A union B equals to 1 and 2 and 3 and 4. Intersection of the sets A and B is the set of all objects that are members of both A and B. For example, set of A and B, A intersection of B equals to 2 and 3. Set difference. The set difference of A and B is the set of all members of A that are not members of B. For example, set A and set B. The set difference of A and B is 1, while conversely, the set difference of B and A is 4. When A is a subset of B, the set difference of B and A is also called the complement of A in B. Symmetric difference. Symmetric difference of A and B is the set of all objects that are a member of exactly one of A and B, which means that it can only appear once in all sets. For example, set A and set B, the symmetric difference is 1 and 4. Let's apply the set theory into Russell's paradox. According to the set theory, any definable collection is a set. Let R be the sets of all sets that are not members of themselves. If R contains itself, then it contradicts its own definition as the set of all sets that are not members of themselves. If it does not contain itself, then its definition dictates that it must contain itself. These two answers lead to contradiction.
You may not understand what's going on here, as the mathematical expressions are quite complicated. You may ask, what is the meaning of translating word problems into mathematical expressions? In the example of using set notation to solve the barber's paradox, we can see that mathematical expressions can help scientists and mathematicians to think and solve paradoxical questions. Okay, let's get back to Zeno's paradox. Both the dichotomy paradox and the tortoise paradox involve the concept of infinity. What is infinity? In the reality, seldom do we have the chance to deal with the concept of infinity. Even we need to count the number of sand in the Sahara Desert. We can say that the required number is a non-zero integer with an extremely large value. But we can find some other non-zero integers larger than that number. We can say that the number is bounded and finite. Then we can define infinity as a concept describing something without any bound. or something larger than any natural number. For example, when we divide a real number by 0, we will get something tends to infinity. Okay, we can now rephrase the dichotomy paradox as follows. Let d be the distance between points A and points B. Before an object can travel from A to B, it must travel through the midpoints of AB, which we denote the points as C. At that time, the object has traveled a distance d over 2. Then the object must travel through the midpoints of CB, which we denote the points as D. At that time, the object has traveled a distance d over 4. This process goes on forever until the object reaches point B. Let fx be the distance traveled by the object after passing through x midpoints. We have. From the expressions, you may think that adding up an infinite number of positive distances should give an infinite distance for the sum. But in fact, all these distances add up to d. It sounds strange, but it is correct. Imagine you have one piece of cake. Periodically, you can share your cake to an infinite number of people. After sharing the cake for an infinite number of years, although there is an infinite number of people having part of your cake, but when you gather the tiny bits together, you can only get one cake, not an infinite number of cakes. You have learned some concepts about infinity and set theory after watching this video. Here is an interesting question. In set A, we have all positive even integers. In set B, we have all positive integers. And in set C, we have all square numbers. In the three sets containing an infinite number of numbers, which set is larger? Why?